And that force, by the right-hand rule and by your cross product, and for this case, looks like this. Now, in a very similar way, basically exactly the same, if we have a current in a wire, that's a charge moving through a wire, and I have a magnetic field, then it's also going to experience a force. So this is my magnetic field, this is my current. Now, current isn't really a vector. I'll describe sort of where our vector comes in soon. But this wire is also going to feel a force in exactly the same way. Well, in a very similar way as we saw the particle in free space moves under experience of a magnetic field. So remember we gave this force. We gave this force as F equals QV cross B. For a current and a magnetic field, a wire and a magnetic field, we're going to give the force as the current, that's I, times L, that's a vector quantity, cross the magnetic field. So here, the vector L, if I'm looking at a wire, is the length of that wire, and that's our vector L. And that length we'll work an example, but that length will have both a magnitude and direction. So it depends the direction of the wire that it is moving with respect to the magnetic field. Often students, when they're doing the right-hand rule for this, it works out exactly the same as what we saw before. They'll just think of the direction of the current and not the direction of the wire, because typically we think of current as having a direction, even though it doesn't, it's a scalar quantity. But if you want to think about it in that way, that's fine, as having an actual direction. Just like we saw, remember with cross products, this is in general true, that if I have a cross product A cross B, the magnitude of it is AB sine theta. And so in a similar way, the magnitude of the force here is going to be the current times the length times the magnetic field times the sine of the angle theta. You can think about the units of this, and you'll see that it's basically the same expression that we saw before. So breaking this down into its basic SI components, remember current is charge over time, and then we have length crossed with the magnetic field. Looking at this little piece right here, this is coulombs per second times a distance, which is meters. And so notice here that what I have is that I have Q times V. So these are exactly the same as what we had before, where we had the force on a free particle in space, the F equals QV cross V. This is exactly the same, except I'm just sort of rearranging my units a little bit, and now expressing the current, which is the charge per unit time, times our length. But the units still work out exactly the same. And it's a very similar thing, because you have these charges that are in a wire, and they're constrained to the wire. They can't move around in free space. They have to stay in the wire, but they still feel a force in the same way as our free particle did. So here I have, my positive particle. It's moving through space, and it moves in a wire with a certain speed, which we characterize by our current, right? Charge per unit time. It moves through our wire. And so because it's moving in a magnetic field, it's going to feel a force. So don't be thrown off by the two different applications, either of the right-hand rule or of our cross product and the way we calculate the force. They're basically exactly the same, except for now our charge is constrained to a wire instead of allowed to flow through free space. We'll see an application for both soon. We'll see an application of this for solenoid switches and also for electric generators. And then we'll also see an application of our particle in free space for a mass spectrometer, where we'll look at the cyclotron equation. Right-hand rule comes up with this again. Y'all try these. You might see one or two more, kind of like you did on the last test. It wasn't a big part of the last test, but you might see it again for the next test, where I have these configurations of I and B. What is the direction of the force? Remember, the force has to be on an axis that's different from either the magnetic field or the current. So here, for example, I have X and Y taken up. So it either has to be plus or minus Z. Here, it has to be what y and z is taken out, so it has to be plus or minus x. And here also plus or minus x. So let's do these as clicker questions. We'll do the first one first, the one on the far left. Hey, Emma. Hey, Brennan. If you're coming in late, don't have your exams for you today. I'll get them to you on Wednesday, okay? I'll hopefully get your grades posted today. I'm hoping to. All right, we're doing the one on the far left here right now. Same as what we did with our QV cross B, index finger in the direction of V, or now we're replacing that with I, where they fold towards or you use your middle finger in the direction of B, and then your thumb gives the force. So same way we did with the other, you're just replacing V with I. All right, let's stop at 110. Yeah, 110. Okay, good. B is right. So fingers in the direction of I, magnetic field is up, so it has to be out of the page. Here we don't have the negative charges being opposite like we did with QV cross B. Remember, if you had a negative charge, you just switch the direction because you don't change your current. And remember also that we consider our current to be a positive charges, and that's true here too. So what was it, B? For the right answer? Or let's try the second one just for practice. Oh, do you know who the first electricity detective was? Sherlock Holmes. Okay, let's stop at 25. And then go ahead and try that last one. Okay, good. B is into the page, and so it's to the right, which is positive x. Try this last one. All right, let's stop at 25. Okay, good. A is right. Current is up. Magnetic field is into the page, or out of the page rather. That's the dots. And so my force is to the right. Also be able to do those things where we switch around. Like I give you force, I give you magnetic field, and you have to find the current, or that sort of mishmash. Let's try this one now. We're going to get into electric generators, and this is sort of teasing on that a little bit, where I'm pushing now a wire through a magnetic field, and I want to know what current is created in that wire. Now remember, our force is equal to IL cross B, and so I want to know now what is the current that's created in that wire. Y'all be working that. I'm going to run upstairs. I'll be back in about 1 minute. Everyone do that. All right, guys, let's see what you got here. I'm going to stop it at 2:55, so go ahead and put in your answer. Were y'all working while I was gone, or were you just chatting? Okay, good. What's that? You fine. Okay, good. A is right. So the way we do this, we just say, our force is 12 newtons. If we impart a force onto a wire and move it through a magnetic field, that will actually cause a current in the wire. So I is what we want to know. L is 1 meter. The magnetic field is 2.4 Tesla. And so my current then is 12 divided by 2.4, which is 5 amps. All right, we'll talk about generators later and how generators work. But in short, this is how they work. I take a piece of wire and I force it through a magnetic field. Or, as we'll see in the next chapter, if I change the magnetic field, that will also generate a current in a wire. We'll see that when we get into induction. Hey, y'all know jokes about sausage? Y'all know any jokes about sausage? They're the worst. All right. I think I have another quick test down here. I'm not really sure if you'll see one like this because we've already done cross products on the previous test, and I don't know if I want to do it again. But let's just try this one. It's really just the task here is that you have to generate a vector for L. So here I have a wire that sits in a magnetic field. This angle is 45 degrees, and this angle is 30 degrees. But actually, to make this a little simpler, we'll just think about there just being one wire. So let's just disregard that first wire. And I want to know what is the net magnetic force if the magnetic field is this and the current is this. Now, I know that F is equal to IL cross B. I know I, that's a scalar quantity, it's 3 amps. And I know B, the magnitude and direction of B. So I need to know what is L. Now, L is a vector, so how would you go about figuring out the vector quantity for L? How might you do that? Can you express L in vector notation, in I, J, K notation? First of all, what components will L have? Will it have I, J, and or K components? It'll have I and J components, right? Because here I have, go back to chapter 1 that we had last semester, chapter 3, I think. I have this vector. It's a distance vector, a displacement vector of sorts. It's a length vector. It has a magnitude and it has a direction, which is given by this angle. And so I can express it in terms of its x and its y components. Y'all know how to do that. It's been a while since we've done it, but you certainly know how to do that. How to express a vector in terms of its x and its y components. So take a few minutes. I'll give you a couple minutes and I'll jump in. But express that vector L in terms of its x and y components. And then take the cross product IL cross B. I want to know the x component of L, and I want to know the y component of L. you go ahead and get L and it's X and it's I and J components, go ahead and start on the cross product. I'll help you in just a minute. But go ahead and do the cross product. You know how to do a cross product.
I don't know where to start.
Remember, you just do FOIL. I cross I is 0. I cross J is K. J cross J is 0. K cross K is 0. I'm sorry, Brandon. I shouldn't have called you that. Okay. All right. Let's. I want to find the X and Y components of L. That's going to be. Well, the magnitude of L is 1.5 meters, so it's going to be 1.5. Gosh, is the X cosine or sine? Right, that's my cosine, adjacent over hypotenuse, right? And the angle here is 30 degrees. What's 1.5 cosine of 30?
1.3.
1.3. And then I have 1.5 sine of 30. That should be what, 0.75, right? All right, so that's my X and Y. So if I express L, I have 1.3I plus 0.75J. So now I do my cross product. My current is 3 amps. That just sort of sets outside the cross product for now. 1.3I plus 0.75J. Crossed with my magnetic field, which is positive 2K. And so now I multiply this, and I multiply this, but I need to know what direction I cross K is. I know I cross K has to be either what or what? Plus or minus J, right? Because they're orthogonal vectors, and so it has to be not I, not K. So it's going to be 3 times 2.6 I cross K. We'll figure out is that plus or minus J, plus 1.5 J cross K. And now, I don't remember these. I mean, mispressed, maybe I could work them out. But I always like to draw my coordinate system over here. And I have I cross K. Use my right-hand rule. K is out of the page, positive K. So that's in the negative J direction. So this is a negative J. And then J cross K looks like it's in the positive I direction. So I have negative J, positive I. Distribute that 3, that's 6, 7.8J, negative, plus 4.5I. And then that's your answer. Now listen, if it did have 2 pieces here, you would just do everything twice. You would find the force on this wire, and then by the same process, find the force on this wire, and you just add them up together. So don't be confused by the 2 wires. But as I said, probably not going to have that on your upcoming test on exam 4. But just sort of as a refresher for cross products, because well, you'll see them in Calc 3 again if you haven't seen it already. All right. Let's look at torque on a current loop, moving sort of into electric motors and generators. May I move down from here? All right. So if I have a loop of wire, it will experience a force. So here I have this loop of wire. It has a current moving through it in this direction, in a, what's that, counterclockwise direction. And my magnetic field is in the positive I direction. Now, 2 of these sides, either the side-to-side ones or the up and down ones, will have no force at all. Which are those? The up and down ones or the side-to-side ones? These right here? What do you think, Jesse? What do y'all think? Josh?
The side to side.
Right, the side ones. because with those, the angle theta is either 0 or 180, and the sine of 0 and the sine of 180 are both 0. If I have two parallel or anti-parallel vectors for B and L, then the force is going to be 0. So I get no force on side A, no force at all. And then on the force on side B, I can calculate that force. It's going to be equal to ILB times the sine of 90 this is the force on this side or on this side. We'll figure out the actual directions, but the magnitude of that force is given by that ILB sine theta. And then the direction on these I can find. So here I have I in this direction are L, but I'm just going to list it as I because students usually find that easier. And B in this direction. So I have I down, magnetic field like this. So the force on the left-hand side is out of the page. What is going to be the force on this other side? Out of the page or into the page? Why is it into the page, Joe? What has happened to this side that's different from this side that causes the force to be the opposite direction? Right, the current has flipped because it's going around in a loop, right? So on one side it goes in one direction, and then on the other, the current goes in the other direction. So here my force is exactly opposite because the current is going in the opposite direction. All right, so on the left-hand side, it's out of the page. On the right-hand side, it's into the page. And then the forces on either side of the loop are going to be equal in magnitude. Because they have the same current, they're in the same magnetic field. So we can calculate the torque. Remember, torque is Fr sine theta. Although in this case, theta is 90 degrees. Remember, torque came about, that was our R cross F. So it's from our cross product. That's why I did that sine theta. We can calculate the torque. It's going to be F1 times A over 2. What I've done there is I have, I'm going to call this F1, and I'll call this F2. I have two forces, though we know that they're actually the same. And then A over 2, that's the length of the moment arm. And so that's why I divide it by 2, because the total length of the side is A, and so I have to divide it by 2. So I have that force times that moment arm times F2 times A over 2. And then that's going to be equal to I times B. B is the length of the wire. So here B is L times B times A over 2 plus I times B times B times A over 2. And so this is equal to I times the magnetic field times A times B. All right, so I haven't done anything really that we haven't seen before. Let me step back through again. This is our torque, force times the moment arm. Force times the moment arm again, because I have two sides, two forces. I add them up, or I replace rather my force with ILB sine theta, but since theta is 90, that goes to 1. So this is I times L times the magnetic field, and then this is our moment arm again. And these all add up to be I times B times A times B. But recognize that the area of this loop is A times B, right? It's just a square. But it turns out, or it's a rectangle, turns out that if your loop is circular, which is usually the case, that the equation would still come out the same with the torque, which is going to be I times B times the area. I'll write it as I, B, A. All right. If we have multiple turns of wire in, usually N is a capital N. Actually, I'm going to rewrite it there as a capital N. If I have multiple turns of wire, then I just multiply it by N. So this is how we can find out the torque that we get out of a, say, an electric motor, for example. If I have a coil of wire that has a certain area, it sits inside a magnetic field, it has a current, and it has a number of turns of wire. I can calculate then the torque output for that electric motor. All right? All right, let's see. Let's try this. Y'all just calculate the magnitude and the direction of the net force on this circuit. Of a circuit of a battery here. I don't think I've seen this symbol before. Sometimes in circuit diagrams, instead of just using one set of lines to represent a battery, they'll use multiple sets of lines. If they have multiple batteries, they'll do this to differentiate between batteries of different voltages. So for example, if they showed a 5-volt battery, they would just show one set of lines. So that's sort of why people use that. We don't usually do that. But let's say that I have a circuit here. It puts a current through this wire over here, and I want to know now what is the force that acts on that wire. What is the force acting on that wire? First thing you want to do is find the current, and then you want to calculate the force acting on the wire. On your test, if you see the force on a current carrying wire, it'd probably be more like this instead of doing a crosswise, since we've already done that. You finish this, you can go into the clicker question on the next page. Just another minute or so, I'm going to jump in there. All right, so first you find your current. What's your current for this circuit? It's going to be 2 amps. Ohm's law, V over R, 10 over 5. 10 volts over 5 ohms. That means that I have a current, I, equal to 2 amps going through this circuit. And then, we just want to calculate our force, ILB. I have 2 amps. My length is this 10 centimeters, which is 0.1 meters, times my magnetic field, which is 2 Tesla. So I get 4 times 0.1, 0.4 newtons. What's the direction of the force? Do y'all know? Well, let's see. I is down, like that, magnetic field. So the force is going to be out of the page. It's going to be towards you. So this wire will feel a force that is out of the page. All right, let's do this clicker question, then we're going to do evals. Here we have something similar to what we've seen before. have this permanent magnet. It creates a magnetic field. Think about what is the direction of the magnetic field. I don't draw it on here, but I give you the poles of the magnet. So what's the direction of the magnetic field? And now what is the direction that the loop turns? At least initially, we'll talk about what that means. But what is the direction that it turns? Good way to approach this is just take one side of it. So you take this side, for example, or this side, doesn't matter, and ask yourself, what is the force on this wire? And then that'll tell you what direction the loop turns, either clockwise or counterclockwise. Finish that up. I'm going to go start handing these out. I'll tell you, y'all have done this routine before, I think. Or not. I'll tell you more about it. Somebody headed over towards the dean's office. Mind taking these over there? I have to leave first. All right, so here our magnetic field runs from north to south. I'm going to stop this at 210. Okay, so go ahead and get your number in, your answer. I'll stop at 213. All right, so here our current is into the page, and our magnetic field is to the left or right, Emma? Which way is it? Is what, Emma?
To the right.
To the right is right, because our magnetic field runs from north to south. So what we have, if I consider this left-hand side, I have a current that is into the page, and a magnetic field that's to the right. And so I go with that. Current is into the page, magnetic field is in that direction, so the force on this side is down. If I do the opposite side, I'll find that the force is up. So this electric motor is going to turn clockwise. Okay? Don't worry about it. We'll do it again next time. But I just sort of want to start to introduce that. We'll look at electric motors and generators next time. All right, so about the